And this is the second lesson in this unit, continuing with circular motion and Newton's laws of motion. This is on page 6 of your unit handout. What we're going to be working with today is not just speed and period or frequency. We're going to be working with centripetal force and centripetal acceleration. So I want to spend a fair amount of time reviewing everything. And this is all typed out for you, but you can just follow along up here. An object that moves at a constant speed in a circular path is moving in a motion that we describe as uniform circular motion. But you need to understand that the velocity is continually changing direction. If you travel in a circle, at every point in time, your velocity is in a particular direction, but even a sliver of a second later, you are pointing in a different direction. So you're moving in a different direction. And that direction is called tangent to the curve. Since the direction of the motion is changing, the velocity is changing. We cannot at this level regress back to grade 9 and 10, where if you see the phrase velocity is changing, you go, oh, it's speeding up or slowing down. That's not what changing velocity means. Velocity is how fast and in what direction. So can the velocity change without it changing speed? Yes, if the direction changes. And that's exactly what we're talking about. So since the velocity is changing, there is an acceleration. We still haven't wrapped our head around what that means. Like, for example, if I tell you the centripetal acceleration is 10 meters per second squared, it's not speeding up or slowing down. What on earth does that 10 meters per second squared mean then? Because if it were accelerating in a line, it would mean you're speeding up by 10 meters per second. But you're not. So today, that's one of the things we'll wrap our head around, is what that number tells you. We learned yesterday that the acceleration is towards the center. And this is the reasoning. And you can read this through on your own time, but I'm just going to explain it. If I'm traveling in this particular direction right now, and if you're watching this on video, you're losing something. You can't see what I'm doing. And there is an acceleration in this direction. I will speed up, won't I? If I'm traveling in this direction and there is an acceleration in that direction, I will slow down, right? What about if I'm traveling in this direction and there's an acceleration this way? Will I speed up? Yes, because some of that acceleration is in the direction that I'm moving. There's only one direction for an acceleration that wouldn't increase or decrease my velocity, and that is this one. Because none of that perpendicular acceleration, perpendicular to the velocity, none of it is in the direction of the velocity or against the direction of the velocity. So that's why the acceleration is towards the center. If it weren't, I would either be speeding up or slowing down, and I'm not. Since F net equals ma, if the acceleration is towards the center, so is the force. And this maybe makes more sense, that if I'm traveling in this direction and I'm being forced in any direction kind of this way, I'm going to speed up. And if I'm forced traveling in this direction, in any direction this way, I'm going to slow down. The force has to be perpendicular to the direction of motion. So what happens is this. I travel in a circle. Bottom line is, if the acceleration is in one direction, so is the net force. That's Newton's second law. So these two things, acceleration and net force, are called centripetal, which means center seeking. Still reviewing from yesterday, if I had a tennis ball being pulled in a circle, and we drew this yesterday, you added in the vectors, we have those three vectors. The velocity is tangent to the curvature. The acceleration and the force are both towards the center. I'm using different colors here to impress on you that these three things are three different types of things. It's not like three forces or three velocities. There are three different types of things. It's apples, oranges, and bananas. So the centripetal force is the net force. This kind of is maybe the most important thing today. The centripetal force is the net force, and it may be the result of an applied force or gravity or friction or anything. But the bottom line is, when I say this in bold, what I mean is this. I literally mean it's the same force. It's not two forces that happen to be equal. And that means, everybody, when you're dealing with circular motion, any place you see F net in a formula, you can write F centripetal. Any place you build a formula and you might have F centripetal that you've written down, you can calculate it by using MA because it's the net force. Also from yesterday here are the formulas. We just went over these, so that's where we are right now. Take a look at the top of the next page, please. I really wish there was a way I could explain this formula to you and where it comes from. And there's a geometric approach that's in your textbook. I don't like it because I think it's a little bit flawed. And the true understanding of it is more of a calculus kind of thing. So without getting into advanced math, I cannot explain to you where this formula comes from. But what I'm telling you is that for the special case of an object accelerating centripetally, moving at a constant speed in a circle, the magnitude of its acceleration can be found by taking the speed squared divided by the radius. It's a fact, okay? And clearly it's a fact. I wouldn't make something up and perform some cosmic practical joke for the past 35 years of teaching people something that's not true. Would have been a good joke, but I wouldn't do that. So this is the formula we use for centripetal acceleration. Just to take a look at this formula in terms of units, it's v squared over r, but v is in meters per second, and r is in meters. This isn't meant to convince you that it's going to be acceleration, but I'm going to demonstrate to you that we do get the same units as acceleration. So when I square, let me get rid of this thing. When I square the meters on the top, I get meters squared over the seconds squared, and it's over meters. The best way to clean this up, and I always do this as a math teacher, not a physics teacher, is to look at it as a mathematical fraction, and we want to multiply the top and the bottom by seconds squared to eliminate this mini denominator of seconds squared. And what's going to happen is you're going to get this canceling happening, and you have meters squared over meters times seconds squared, but then a meter on the top and the bottom cancels, and you're left with the units of meters per second squared. Okay. Again, that's not meant to prove to you that the formula works. It's meant to demonstrate that we get the same units. So we're just going to get into some questions and examples. Use the formula above for centripetal acceleration and this formula to find a new formula for centripetal acceleration. So what do I mean by that? Well, just wanted to make sure I was recording. The centripetal acceleration is equal to v squared over r. And I tend to not use vector symbols with circular motion at all. Normally I would put a vector symbol in the absolute value signs, right? But the reason why I'm not going to is we would never want to use the vector symbols anyway. I can't talk about a singular direction for the acceleration. It's always towards the center. So that direction is different depending on where the object is. There's no sense even talking about vectors here. But we also know that v equals 2 pi r over t. This is that. So I'm going to do an algebraic substitution. I'm going to take this thing and put it in here. And what's going to happen is I'm going to get the centripetal acceleration equals 2 pi r over t, quantity squared over r. So I'm going to square the 2, I'm going to square the pi, I'm going to square the r, I'm going to square the t, and I'm left with a equals 4 pi squared r squared over t squared over r. Capiche on that step? You see what I've done there? Okay, again, from a standpoint of a math teacher, and you know if you have me for Math 20, I've used this terminology before. I don't know if Mr. Hetlinger uses it, but this is called a complex fraction. This line that I've drawn here is the main fence between the numerator and the denominator. There's a word for that line and it escapes me. It's a weird word. Okay? That line is the fence between the numerator and denominator. In fact, let me distinguish it that way. So we have a numerator and we have a denominator. But what makes this a complex fraction, and I'm explaining this to you to help you out in your math class as well, what makes it a complex fraction is there's a denominator within the numerator. And if there were a denominator within the denominator, that would be complex as well. So our goal when we have a complex fraction mathematically, and this is math, this is math that we're working on right now. Our goal when we have a complex fraction is to eliminate that pesky mini denominator. So how can I get rid of that t squared? I can multiply the numerator by t squared and the denominator by t squared. This is the most efficient and best way to clean up a complex fraction. So what we get is 4 times pi squared times r squared over r times t squared, because what happens is this t squared cancels with that t squared. And now in the numerator you just have that 4 pi squared r squared, and in the denominator you have r squared t squared. This is equal to a. I shouldn't need to, and you certainly don't have to, write r squared is r times r, but I'm just giving, I'm taking the opportunity to explain something which I've talked about numerous times in my Math 20 class. In fact, just yesterday we talked about it. You were allowed to cancel things when they are factors. And on the top of this, I have a factor of r, and on the bottom I have a factor of r. What makes something a factor is it's in brackets multiplied by everything else. If you're in my Math 20 class, you recognize what I'm talking about. Right? So where does that land us? It lands us at a equals 4 pi squared r over t squared. This is a centripetal acceleration formula. And we knew that centripetal acceleration is v squared over r. So I guess what I'm telling you is you have two ways in which you can calculate centripetal acceleration. One is to use v squared over r, the other is to use 4 pi squared r over t squared, which is not something you have to memorize when you look at your formula sheet. I'm going to go to your formula sheet right now. I know I got it here somewhere. There it is. When you go to your formula sheet, under kinematics, you see v equals 2 pi r over t. And then I don't like that they've smeared these two equations together. I really don't. I would rather it said a equals v squared over r, and then below that, a equals 4 pi squared r over t squared. But those are the equations. Notice, everybody, and I'm kind of going around a little bit in circles here, no pun intended. Notice no place on your formula sheet do you see a formula that says FC. Why not? Why is there no formula for centripetal force? Yep. Right, the net force is your centripetal force. So, and I will get back to your notes in a second, but when you take a look at your dynamics section, you have this formula, right? I don't think I have it up here. You have this formula under dynamics, correct? And this is the way it's written. Well, if I ever say, what is the centripetal force, your brain's going to say, I need to find the net force. Because the net force is the centripetal force. And again, everybody, you understand that I much prefer this. Okay. In fact, as I've said before, it surprises some students in Physics 30 when they look at their formula sheet and they don't see it there. It's like some misremembering thing. It's never that. It's the one on the left. But we use the one on the right. So now I want to get back to your notes here. Question 1, we've determined now there are 2 formulas we can use to calculate centripetal acceleration. Question 2 says, what would you do with the centripetal acceleration to determine the centripetal force? And I've covered up the hint. What do you do to calculate the centripetal force? Well, the centripetal force is the net force, right? And that's what I've covered up here. I've given you the hint that centripetal force is the net force. The net force is found by using ma. So the answer to this question is this. And again, F sub c is not a unique force. If you look on your formula sheet, you will find F sub g someplace. You will find F sub F someplace because there is a way to calculate gravitational and frictional forces. If you look under electricity and magnetism, you'll find at least one formula that is F sub E, which means electric. And if you look under electricity and magnetism, you'll find a couple of formulas for F sub M, which is magnetic. You will not find F sub C because it's not a type of force like the others are. What F sub c is the net force. So this is what you do to the acceleration, the centripetal acceleration, to find the net force. So now you've got the following formulas. That, this, and this, and these are on your formula sheet. What's not on your formula sheet are these 2. And I want you to ponder what I've done there. That the centripetal force will have a magnitude of the mass times v squared over r. Why? Well, because v squared over r is the centripetal acceleration. And Fc is really the net force, which is mass times acceleration. Same thing here, right? This is the centripetal acceleration. So you multiply the acceleration by the mass to get the net force, which we can call the centripetal force. But those are not on your formula sheet. So now let's put this into action. Number 1, a 50-gram mass is in a centrifuge. How many of you know what a centrifuge is? What a centrifuge is something that you put a test tube in, and the test tube is at an angle, and the top of the test tube would be where my shoulder is, and it spins very rapidly. And what happens is the different layers of the material get separated. And over time, we'll discuss what's really going on here, but let's just worry about the formulas right now. The centrifuge rotates at 300 RPM, and you're given the radius. Find the centripetal acceleration and the centripetal force. Let's start with that. So we can find centripetal acceleration using v squared over r, or 4 pi squared r over t squared. What do we know? We know the mass. I'm pretty sure that everybody understands we're going to use the mass when we want to find the force. What else do we know? We know the radius of curvature is 6.5 times 10 to the negative 2 meters. And we can find the period. So one of the things we focused on yesterday was if you had RPMs, how can you find the period of revolution from that? Well, 300 revs per minute is a frequency. This is a frequency. It's not the frequency with standard units, but it is a frequency of rotation. What do we have to do to that to get it into revs per second, which is the standard? Divide by 60. So of course, if you take 300 revs per minute and you divide by 60, everybody knows you're going to get 5, because 300 divided by 60 is 5. So it's 5 hertz, which actually isn't that fast. Like, it's 5 times per second is pretty fast. So what are we going to do to that to find the period? Well, the period is the reciprocal of the frequency, so that will be 1 over 5 hertz, which is 0.2 seconds. Now, well, I'm just going to ask everybody here. You're asked to find the acceleration, and we know r and we know t. How many of you would use this second formula to find the acceleration? How many of you would use the first formula, but you would find the speed first? I would. Just the way my brain operates, I would use this formula to find the speed, then I would square it and divide it by r. I think at this point in the course, though, using formulas is easy. I'm going to do this on a calculator. I'm not going to write down a whole bunch of stuff. So if you use the blue formula, and given my mistake with division earlier, is this correct, 0.2? Okay. So I'm going to use the blue formula. I'm going to take 4 times pi squared times r divided by t squared, and this is going to give me the acceleration, 4 pi squared r over t squared, and it gives me a centripetal acceleration of 64 meters per second squared. Good? Okay. And I don't know why. You know what it might be? It might be that when I took physics way back when, we weren't given this other formula. I don't know. I just prefer to go 2 pi r over t So I'm going 2 pi r over t to find the speed, and then I square that, and I divide by t squared. Divide by r. Okay, but we're able to get 64 meters per second squared. Okay, so we know the acceleration. The centripetal acceleration has a magnitude of about 64 meters per second squared. How are we going to find the, quote, centripetal force? Well, we're going to say that it's really the net force, which will be the mass times the acceleration. I just need to multiply this by the mass. I believe the mass was 50 grams. Yes? 0.05 kilograms. 3.2 newtons. Now, this is going to be an explanation which is an in-depth explanation. It's not a simple explanation to either provide or understand. But the thing I want to begin with, we're asked to compare this to what happens on the surface of the Earth. The thing I want you to understand is if you were in that centrifuge and you had a mass of 50 grams, you would be experiencing this acceleration and you would experience this force. But I want you to understand, it's easier to understand what's going on by talking about the acceleration. Okay? Do you agree right now that when you're sitting there in your desk, you are experiencing a weight? Okay? And the weight you experience, we've talked about this before, is a force upwards on your butt. That's why if you sit in a desk for too long, your butt gets sore. Okay? It's gravity that's pulling you down, but you feel the force up. Just like, day one we talked about this, if you're in a vehicle that suddenly slows down, you feel forced forwards. But the force on the vehicle is actually in the other direction. So when I'm in a vehicle and it slams on the brakes and the seatbelt pushes against my chest, I feel that force backwards against my chest, but it's not really that. It's that force that I'm feeling, but I feel as though I'm being pushed forward. Okay, so I feel opposite. How many times greater than the acceleration due to gravity is this acceleration? I want you to do a calculation here. I realize that some of you probably came up with a number in your head, but if I take that number divided by 9.81, I'm going to get about 6.4, but I'm going to guess 6.6, 6.5. So this centripetal acceleration is about 6.5 times the acceleration due to gravity, which I experience the acceleration due to gravity as feeling a weight. So what I'm going to ask you to imagine is a ridiculous scenario where this is the centrifuge and it's spinning around and you are standing on the inside of the centrifuge. Every part of the centrifuge is being pushed, this is hard to imagine, is being pushed towards the center. So this is pushing against your feet. No matter where you are, if at some later point in time you happen to be here, then it is pushing against your feet towards the center. You would be able to walk around on the inside of it. Not very easily, because the acceleration you would be experiencing is over 6 times the acceleration due to gravity. You would feel 6.5 times as heavy as you would on Earth. Do you get my drift here? So this would mean that your apparent weight, which is the applied force to your feet by what you're standing on, would be about 6.5 times your true weight. Centripetal acceleration, it can always be thought of in that way. If I told you that something experienced a centripetal acceleration of 10 Gs, that's a really rapid acceleration. That would mean you would feel 10 times as heavy if you were inside of that orbiting drum. So this is the bottom line. The centripetal acceleration is 6.5 times the acceleration due to gravity. And you arrived at that, I hope, by just taking 64 divided by 9.81. Let's take a look at another example. A Blu-ray disc has a diameter of 12 centimeters. What is the centripetal acceleration at the edge of the disc if the period is 0.1 seconds? Well, this time what I will do to find the centripetal acceleration is just use the formula that takes me there the quickest. Did I write that down correctly? Where did the 0.06 come from? Ethan, do you know? The radius. That 12 centimeters is the diameter. We need to divide it by 2 to get a radius. So I'm getting 237 meters per second squared. So again, this is what I talked about at the beginning. We understand what meters per second squared means when you speed up or slow down. It means meters per second per second. If it's centripetal, where the acceleration is perpendicular to the motion, what it means is a comparison between that number and 9.81 to wrap your head around. Would you agree this is approximately 24 to 25 Gs? It's quite a big acceleration. If you were inside of a drum experiencing that centripetal acceleration, and here's something I didn't talk about yet, but I would feel that force against my feet that's 25, roughly 24 to 25 times more than I would on Earth, right? But what do I think I feel? I feel pulled down, don't I? Just like when the seatbelt pushes against my chest, I feel forced forward. That's it. During a roller coaster ride, a car moves through a circular portion of a track with a radius of 15. How fast is the car moving if the centripetal acceleration is 25 meters per second squared? Well, pretty easy question. Most of this stuff today is just you getting used to the formulas. A equals v squared over r. So we can put 25 here. The radius is 15 meters. You just have to take 15 times 25 to get v squared. Doesn't matter what 15 times 25 is, we're just going to take the square root anyway. About 19 meters per second. Still good? All right. Well, the next set of questions is going to have a lot of calculations, but rather than do them over and over again, we're going to do the set of calculations once and then use some features of our calculator to make it simpler. A 1,600 kilogram car rounds a curve on the highway with a radius of 50 meters. What's the centripetal acceleration in all of these cases? Okay. So the first thing to do is we need to divide this number by 3.6 to get meters per second. Which is 19.4. Repeating. Meters per second, and then we would use v squared over r. So I need to square that speed divided by the radius of 50 meters, and I get 7.6 meters per second squared. We are also asked to calculate the force. Well, how are we going to calculate the force? ma, sure. The centripetal force is the net force, which is ma. So this is the acceleration, and now if I multiply that by 1,600, I get the force of 12,099 newtons. So we have to repeat that for all of these. But if you focus up here, what we can do instead is go stat, edit. Well, I have a whole bunch of stuff in my lists. Can you go stat, edit, and see if you have anything in your lists? Any remnants of anything? If you do, go to your memory management menu, which is second plus, and clear all lists. So now stat edit will show empty lists, and I'm simply going to put in all of my speeds in list 1. I want to double check though. Are these the same speeds on your handout that I have up here? Okay. So now I'm going to quit out of here. What was the first thing we did? We converted that kilometers per hour to meters per second. So I'm going to do that by going second 1, which is list 1, divided by 3.6, and I'm going to store the answer as list 2. I could scroll over here and see what all of these numbers are, but what they are going to be are all of the speeds in meters per second. In fact, if I go to my list again, I see now that list 2 is populated with those speeds. What did we do then? I'm going to quit out of here. Well, then we took the speed squared divided by the radius. Well, I'm going to take the speed, which is now in L2, so I go second 2. I'm going to square it and divide by the radius of 50. And if I hit equals right now, I will get all of those accelerations. Right? There they are. But I need to store them. So this is a different way you can do it. You can hit enter and then go store. I need to store that someplace. I'm going to store it as L3. It seems to me we've done this before. I can't remember with what. Some data on a lab maybe. And now if I were to go to stat edit, this list is the acceleration of those 5 situations. What did we do then? Well, I'll quit out of here. We took those accelerations, which are list 3, and we multiplied by the 1,600 kilograms. These are the forces. Well, I'm going to store it as L4. If I store it as L4, it's just easier for me to look at them. Like here, if I want to look at them, I have to scroll around. If I store it as L4, I can go over here to L4. So the bottom line here, everybody, is these are the accelerations, these are the forces for 70, 80, 90, 100, and 110 kilometers per hour. I'm not overly concerned about your ability to use lists. What I'm concerned about is the physics, and the list is just a way for us to lighten the load and do less work. If you were asked to compare the accelerations to the acceleration due to gravity, we would be dividing all of these accelerations by 9.81 to find out how many g's. Which would mean, I guess I could take L3, quit out of here first. I could take L3 and divide by 9.81 and maybe store it. You know what? At this point in time, everybody, if you want, you can store it as L2. We're done with L2, aren't we? The reason why I'm suggesting that we do that is when I do that and go to my lists, I can see the answers to this question right next to the speeds. So at 70 kilometers per hour, you were experiencing about 3/4 of a g. Think about that for a second. What that means, and let's say you're in the passenger seat and the car is curving to the left. Somebody else is driving. You're going, are you going slow enough? And they go, yeah, yeah. And they enter the curve, and the car experiences an acceleration of 0.77 g's. That means the door that you are leaning against is pushing against your right shoulder with 0.77 g's. which means you will feel 3/4 of your weight pushed against the door. If you're driving, the person has to really hang on to the wheel because they will be forced in their mind outward. What's actually happening is they're going this way and the car is moving away from them, so they continue in a straight line. I hope you see that forgetting about friction and the ability for your car to stay on the road, this is too fast. You would be experiencing close to 2 G-forces if you were traveling at 110 kilometers per hour around a 50 radius curve. So you would have a hard time maintaining control of the vehicle physically.